So, welcome to a series of lectures on mathematical methods and its applications. We were discussing Laplace transform and their properties. So, in this lecture we will see that what are the initial and final value theorems for Laplace transforms and how they are important to find some Laplace transforms of some functions. Okay. Now, what is initial value theorem? Let us see. Let Laplace transform f t is suppose f p and f dash t be piecewise continuous and is of exponential order for t non-negative, t greater than or equal to 0. If limit p tends to infinity p f p exists, then this theorem states that limit p tend to infinity p f p is nothing but limit t tending to 0 f t. So, this is initial value theorem. Now, what is the proof of this theorem? Let us see. So, what is Laplace of f dash t? So, it is nothing but we already know that it is nothing but p f p minus f 0. Laplace of f dash t is nothing but p f p minus f 0, where this f p is nothing but Laplace of f t. Okay. So, this f p is nothing but Laplace of f t. Now, let us compute Laplace of f dash t by the definition and take limit p tending to infinity, because in initial value theorem we have to take limit p tending to infinity. Okay. So, what is Laplace of f dash t by the main definition of Laplace? It is nothing but 0 to infinity e की power minus p t f dash t into dt. Okay. And this is which is equal to, by this it is equals to p f p minus f 0. So, take limit p tend to infinity both the sides. So, it is limit p tend to infinity of 0 to infinity e की power minus p t f dash t dt will be equal to limit p tending to infinity p f p minus f 0. Now, let us compute this part. Let us compute this part. Now, f dash t is of exponential order and is piecewise continuous. So, mod of f dash t will be nothing but less than equals to some m into e की power alpha t. There will exist some m and alpha such that mod of f dash t will be less than equal to m into e की power alpha t, since it is of exponential order alpha. So, we can easily write that this value, the left hand side, okay, the left hand side 0 to infinity e की power minus p t f dash t dt and its modulus will be less than or equals to 0 to infinity e की power minus p t mod f dash t into dt, and this mod f dash t is less than equal to this because it is of exponential order alpha. So, it is again less than equals to 0 to infinity m into e की power minus p t into e की power alpha t dt, and this quantity is nothing but m into integral 0 to infinity e की power minus p minus alpha t into dt. So, this integral is nothing but it is m into e की power minus p minus alpha times t upon minus p minus alpha times t 0 to infinity. So, when p is greater than alpha, so this value is nothing but 1 m upon p minus alpha, because when p greater than alpha and t tend to infinity, this will tends to 0, and at 0 this will tends to 1. So, this will nothing but m upon p minus alpha. So, basically this expression is less than equal to this expression, okay. And when p tending to infinity, so this will definitely tend to 0. So, hence this tends to 0, okay, because this expression is less than equal to this expression m upon p minus alpha, and as p tending to infinity, this expression will be less than equals to limit p tend to infinity this expression, and as p tend to infinity, this is tending to 0, which is tending to 0 as p tending to infinity. So, hence we can say that limit p tending to infinity 0 to infinity e की power minus pt f dash t dt is equal to 0. Now, using this fact in this expression, what we will obtain? So, if we use this fact over here, so this is nothing but 0, okay. We have just proved that this expression is nothing but 0. So, from here we will obtain that limit p tending to infinity p f p is nothing but f 0. Now, when we proved this property of Laplace transform derivatives, that Laplace transform f dash t is nothing but this expression. So, there we have assumed that function is continuous for all t greater than equal to 0, okay. So, if function is not continuous, that is why we are obtaining f 0 over here, because we are assuming f is continuous throughout non-negative side of real axis, okay. So, that is why we are obtaining f 0 over here. If function is not continuous at t equal to 0, then instead of obtaining f 0, we will obtain limit t tending to 0 f 0 over here, f t over here. Instead of this expression over here, we will obtain this expression if f is not continuous at t equal to 0, okay. So, basically things are same. If function is continuous at t equal to 0, so this is nothing but f 0. However, if function is not continuous at t equal to 0, so this is nothing but this expression nothing but f 0 plus on the right hand side of t equal to 0, okay. Take the right hand limit of t equal to 0, that is f 0 plus. So, therefore, to generalize this theorem, we are writing on the right hand side, we are writing limit t tending to 0 f t, because if function is continuous, the right hand side will definitely be f 0. If function is not continuous at t equal to 0, the right hand side is nothing but f 0 plus. So, in both the cases it will work, okay. So, that is why we are writing limit t tending to 0 f t in the right hand side instead of writing f 0, okay. So, this is initial value theorem. Now, we will come to final value theorem. Now, what final value theorem states, let us see. If Laplace transform f t is f p, suppose, and f dash t is piecewise continuous for t greater than equal to 0, and if limit t tend to infinity f t exists, then this result hold. Now, what this result is? So, this was initial value theorem, and what is final value theorem? It is limit p tending to 0 f p f p is nothing but limit t tending to infinity f t. So, this is final value theorem. So, let us now prove the final value theorem. How we will obtain final value theorem, let us see. Now, again we will go to the same expression. What is that? Limit Laplace transform f dash t is nothing but p f p minus f 0. So, again this f0 will be limit t tend to 0 ft if function is not continuous at t equal to 0, okay. And this Laplace transform f dash t is nothing but, from the definition of Laplace transform, 0 to infinity e की power minus pt f dash t into dt. Now we want limit p tend to 0, okay, this side. So same here, same on this side also. So this is equal to p fp minus f0. Here we are assuming f is continuous at t equal to 0. Take limit p tend to 0 both the sides. So what we will obtain? Limit p tend to 0, 0 to infinity e की power minus pt f dash t dt, and the right hand side will remain the same, limit p tend to 0 p fp minus f0, okay. So now if p tend to 0, this will tend to 1. So this side is nothing but, this implies 0 to infinity f dash t dt, which is equals to limit p tend to 0 p fp minus f0. Now let us see the left hand side. What is left hand side? Left hand side is 0 to infinity f dash t dt, okay. This is right left hand side. So what this expression is, basically this is something limit k tending to infinity 0 to k something f dash t dt. Now since derivative integral is antiderivative, we already know this. So this is nothing but limit k tending to infinity f t from 0 to k. So this is nothing but limit k tending to infinity f k minus f0, okay, and which is nothing but, we can simply write limit t tending to infinity f t minus f0. This we can simply write like this. So this is left hand side. So left hand side is equal to this expression. So when we equate both the sides, so this will be equal to, from this side is nothing but limit p tending to 0 p fp minus f0. So f0 cancel from both the sides. So this we obtain this result, which is final value theorem, okay. If function is continuous at t equal to 0, we are having f0 over here. If it is not continuous at t equal to 0, we will be having f0 plus here also and here also. So in both the cases, whether function is continuous or not at t equal to 0, f0 or f0 plus will cancel from both the sides, okay. So finally we will be having this expression which we are calling as final value theorem, okay. Now let us see some of the problems based on initial and final value theorem. First of all, let us illustrate a simple example of f t equal to 2 e की power minus 6t. Let us illustrate this using these two theorems. So one can easily illustrate this very easily. You see that first is, suppose initial value theorem. Suppose first is initial value theorem. Initial value theorem. First, suppose you want to illustrate this theorem using this example, for this example, sorry. So what is f t? F t is 2 e की power minus 6t. So what is Laplace of f t? Very simple, it is 2 upon p plus 6. So this we are calling as fp. Now see initial value theorem, the left hand side of initial value theorem is limit p tending to infinity p f p. So what is limit p tending to infinity p f p? P into f p, so that is 2 p upon p plus 6, and as p tends to infinity, this will tends to, you divide numerator and denominator by p, this is this quantity and this will tends to 2. Now the left hand side, limit t tending to 0 f t. So limit t tending to 0, what is f t? 2 e की power minus 60, so it is nothing but 2. So hence initial value theorem has been verified, because left hand side is equal to right hand side. Okay. Now come to final value theorem for the same problem. So now the final value theorem. So what is left hand side for final value theorem? Limit p tending to 0 p f p. So it is limit p tending to 0, p f p is 2 p upon p plus 6 and it will is equal to 0, it is clearly equal to 0. Now what is limit t tending to infinity f t? It is limit t tending to infinity, f t is 2 e की power minus 60, which is obviously 0, because at t tends to infinity e की power minus t tends to 0. So that will tends to 0. So hence since left hand side equal to right hand side, hence the final value theorem has been verified. So the first problem has been solved. Now come to a second problem. Given that f p is this, okay, find f 0. So we already know f p, which is Laplace transform of some f t, okay. Now without finding Laplace inverse, we can easily find what is f 0. How? Using initial value theorem. So here here we are assuming that function is continuous at t equal to 0, okay. Then only we can obtain f 0, okay. So what is f p for this problem? What is f p given to us? It is p plus 3 upon p plus 2 whole square plus 3 square. This is f p. Now what will be, what is f 0? F 0 is nothing but by the initial value theorem is f is continuous at t equal to 0, f 0 is nothing but limit p tending to infinity p f p. So it is nothing but limit p tending to infinity p into f p, p into f p. So this you can easily see that this limit will tends to 1. So it is equal to 1. So what is the value of f 0? Is 1. So without finding Laplace inverse of this function, we can easily find out what is the value of f 0 using initial value theorem, okay. Similarly, if you want to find out limit t tend to infinity f t, so that also we can find out using final value theorem. So limit t tend to infinity f t will be nothing but using final value theorem, it is equal to this expression, limit p tending to 0 p f p, and it is nothing but limit p tending to 0 p into f p is p plus 3 upon p plus 2 whole square plus 9, and it is nothing but is equal to 0. So limit t tend to infinity f t is nothing but 0. So that also we can find out using initial and final value theorems. Now let us solve some problems which we have already discussed in the previous lectures, that how to find Laplace transform of these functions, but let us find these function using initial value theorem. Let us solve first problem, okay. So I am telling these problems over here because these theorems will play an important role while we solve some differential equations. So that is why we must have information about what initial and final value theorems are and how they are important and how we can solve problems based on this, okay. So how to find Laplace transform of this function 0 to t, it is sin u upon u du. So, so we already see that how to find Laplace of this. We first find Laplace of sin u, sin t, which is 1 upon p square plus 1. फिर sin t upon t is given by integral p to infinity fp dp, okay, and then for 0 to t it is nothing but fp by p, which is fp is Laplace of this entire function. So, that we have already discussed in the last lectures. Now, how to find Laplace of these functions using initial value theorem, okay. So, let us see. Now, let us call this whole function as ft. So, ft is equals to 0 to t sin u upon u tu. So, what is f dash u? Derivative of f respect to t, that we can find out using Leibniz theorem. So, what will be the derivative of this? It will be sin t by t into 1 minus 0, okay. So, that is quite obvious that this will be this, and of course, one can easily see that f0 is nothing but 0, because when you take t tending to 0 or t equal to 0, so this lower and upper limit both are same, value will be 0, okay. Now, here t f dash t is nothing but sin t, t f dash t is nothing but sin t, okay. Take Laplace both the sides, so Laplace of t f dash t is nothing but Laplace of sin t, okay. We are interested to find out Laplace of ft, okay. We have to find out Laplace of ft using initial value theorem, okay. Now, Laplace of t into some function is nothing but, we already know that Laplace of t ki power n into some function say ft is nothing but minus 1 ki power n d by dp of fp, where fp is nothing but Laplace transform nth derivative, sorry, nth derivative of fp, where fp is nothing but Laplace of this ft. Now, here in place of ft we have f dash t. So, what will be this expression will be minus 1 ki power 1, n is 1. So, it is d by dp of Laplace of f dash t, and what is Laplace of sin t? It is 1 upon p square plus 1. Now, this is further equal to minus of d by dp of Laplace of f dash t is Laplace of f dash t is p f p minus f 0 is equals to 1 upon p square plus 1, okay. So, this expression further can be written as minus d by dp of p f p is equal to 1 upon p square plus 1. Derivative of this with respect to the p will be 0, it is a constant quantity, so derivative will be 0. Now, it is nothing but minus p f p is equals to, take integration both the sides respect to p, so it is tan inverse p plus some arbitrary constant c, because it is an indefinite integral, okay. Now, how to find c? So, to find c, take limit p tending to infinity both the sides, okay, limit p tending to infinity both the sides. So, it is limit p tending to infinity minus p f p, it is limit p tending to infinity tan inverse p plus c. Now, this quantity is by the initial value theorem is nothing but limit t tend to 0 f t, and limit t tend to 0 f t, which is f 0 here, is nothing but 0, okay, which is nothing but 0. So, we can say that this is 0, because this expression p f p limit t tend to infinity is nothing but t tend to 0 f t, and limit t tend to 0 f t is f 0, which is 0, okay. So, this is 0 and this is pi by 2 plus c. So, c is nothing but minus pi by 2. So, what will be Fp from here? So, Fp will be nothing but minus 1 by P times tan inverse P minus pi by 2. So, and what is Fp? Is Laplace transform of Ft. So, hence Laplace transform of this Ft is nothing but this. So, basically initial Fallot-Vallon theorems are important to find out this arbitrary constant C, otherwise it is difficult to find. Okay. Hence this Laplace transform of this Ft is nothing but this expression. Now, let us compute the second problem. This problem can be solved also using initial value theorem. E की power it is u sin square u upon cos upon u into du. So, again you will take this function as say Ft and try to find out its Laplace transform using initial value theorem on the same lines as we did earlier. So, take this as Ft. What is Ft? Ft is 0 to t e की power u into sin square u upon u into du. Okay. So, what is f dash t? Is e की power t sin square t by Leibniz theorem, and of course limit t tend to 0 f t, or we are calling as f 0 is nothing but 0. Okay. So, take t in the right hand left hand side. So, it is this expression. Take Laplace transform both the sides. Laplace transform of left hand side is minus 1 की power 1 d by dp of Laplace transform of f dash t. Now, to find Laplace transform of this expression, first find Laplace transform of sin square t and then apply first shifting property. What is Laplace transform of sin square t? Laplace transform of sin square t. This we can find out Laplace transform of 1 minus cos 2t by 2, and it is nothing but 1 by 2p minus 1 by 2 into p upon p square plus 4. So, it is nothing but, and again apply shifting property. So, you replace p by p minus 1. So, it is 1 upon 2 times 1 upon p minus 1 minus p minus 1 upon p minus 1 whole square plus 4. Okay. You replace p by p minus 1. Now, minus of d by dp of it is p f p minus f 0, which is 1 by 2 of 1 upon p minus 1 minus p minus 1 upon p minus 1 whole square plus 4. Derivative of this with respect to p is 0, so it is minus p f p. You integrate both sides respect to p and derivative of this is 0. Okay. So, this is 1 by 2 comes out, this is log of p minus 1 and multiply and divide by 2. So, it is minus 1 by 2 log of p minus 1 whole square plus 4. So, from here f p is nothing but and plus c also, because it is an indefinite integral. Okay. So, f p is nothing but minus 1 by 2 p. Okay. Take p over here only and 1 by 2 it is log p minus 1 upon under root p minus 1 whole square plus 4 and plus c. Now, you can use initial value theorem to find out the value of c. Take limit p tending to infinity both the sides. As p tend to infinity, this side will be equal to limit t tend to 0 f t, which is nothing but 0. So, this side will be 0, as p tend to infinity, this will tends to 1 and log 1 is 0. So, c is nothing but 0. So, c will be 0, okay, and fp can be find out. So, fp will be nothing but you divide this by minus p. So, f and fp is nothing but Laplace transform of this ft. So, hence we can find out Laplace transform of this function. So, similarly the third problem can also be solved using the same concept and initial value theorem. So, thank you very much.